Welcome back. In part 2 of the demo, we're going to have a look specifically at the steering behaviour that we had or elicited within the game. So in particular for the two turrets that we have here, about how they rotate and look towards the player, and for the seeker ships that we have flying around, about how they seek towards the player but also then try to avoid the other objects. Just as a small aside to that, in terms of the viewport, so you see whenever I sort of flying through the level, you have the player in the center of the level. Now if I were to try to go down to the bottom, I'm bumping against the bottom of the screen, so I can't move out. But you'll also notice that the viewport itself stops as well. So the minute the viewport here is focused on the player and the viewport's moving, as soon as the viewport stops moving, which for example happens here, then I'm still trying to center the viewport on the player, but because the viewport would fall outside the screen, I'm then repositioning it back into the center so the whole viewport is visible on it. And you can also see that whilst the player I can't move the player out of the level, the AI spaceships, they actually are permitted to leave. So that's just how it was done. Right, so let's have a look at the remaining classes in this. It comes down to our AI controlled spaceship, our player controlled spaceship, and then we have a bunch of steering behaviors. So we'll do the player controlled spaceship first of all. So it's a type of sprite, so it has something that can move around the level. This player controlled spaceship, it gets input, so it's looking for input from the player. And the particular mechanism or vehicle that it uses, I'll go back to this one here, is really based on where the touch event occurs relative to the center of the screen. So we have the center of the screen. If I tap over here, then it's going to bring me straight across, because relative to the center I'm off to the right. Over here, relative to the center I'm off to the left. This will be straight up, more or less if I get in the center, and this would be straight down, more or less in the center. And if I click over this corner again, so it depending on where the click occurs relative to the center, it's going to fly me around the game. So I need to know where the center is, and that's what I store within this particular vector. And I have another vector for the acceleration that the touch input is providing. So that's all I need beyond what I'm getting through inheritance. Here's my constructor. So I take in a start location, and I take in a screen, and I'm giving it a default 50 by 50 size. I'm saying that you use this particular image, and I'm passing those off to the sprites constructor so it can store them. Once I do that, then I say, okay, I need to know where the center of the screen is, so I'm going to the screen that I belong, I'm going to the game that screen belongs in, and I'm asking what's the width and height of the screen, and then using that. If you remember back to the sprite class, we had maximum values defined, and if I didn't, and the maximum values are defined were actually incredibly large, and they're as large as you could get. If I had a very large maximum value, what that means is if I held down the button, it would just accelerate faster and faster. So this gives me a way of controlling just how fast the ship can accelerate and how fast it can move across the level. So by changing these, if I say maximum acceleration, let's give us 500, and we want to be a bit faster in terms of how quick we can accelerate, and I were then to run that again, now my player is able to zoom across the level at a much faster pace. So it's going to be those properties that will enable us to depending on the game, to control just how responsive or fast or whatever, how quickly it can turn you want the thing to be. So we define them there for the acceleration of velocity and how quickly it can turn and how quickly it can accelerate in terms of turning as well. They're arbitrary values, so they were sort of just picked, so they looked reasonable in terms of the demo. The update then, the other method we have then is an update. We have no draw, so we're using the draw that we inherit from sprite because that was good enough. In update, we're checking for input. So we go to our screen, to our game, and get the input manager. We check to see, do we have input? And this is set up, it assumes single touch input, so we're not looking at multi-touch here. In fact, if there are multiple touches, you've got a question of, okay, what acceleration do you use? So there we're just going to use the primary input. Is there sort of exists touch ID 0, or the first one? If so, then we get that input and we turn it into an acceleration. And the further away from the center, the greater that acceleration is going to be. You'll notice here that this is the x location, take away the center x location. That kind of makes sense. So if x is, say, a value, say it's 1,000, I don't know, 1,000 pixels across. So the middle position would be 500. If I clicked over on the left-hand side, it would be a value of minus 500. So we're trying to go minus 500. Over on the right-hand side, 1,000 minus 500, 500 in the opposite direction. If you're looking at the y coordinate here, you'll notice it's the other way around. This is touch, take away center. This is center, take away touch. And the reason for that is because in terms of the screen coordinates, positive y is down the way, but in terms of our world, positive y is up the way. So I'm inverting it around there so it maps onto the assumptions about direction within the world. We then convert that into our acceleration, and effectively we're sort of scaling it by the maximum acceleration that we have available. So this will be in the range, sort of minus 0.5 up to 0.5, and then we scale that up as need be. Angular acceleration then, once we've got our input, we know which, the direction we're going to accelerate in. We also want to make sure the player ship points in the direction of movement. So we're going to one of our steering behaviors, and this is the library we'll have a look at in a second. And we're saying align with movement, and we're passing in this object. And what that method will do is it will give you as an output the angular acceleration that you should use if you want to align with your movement. So this is what we are using for our angular acceleration. It's a value we inherit from Sprite. The next thing we do after that is apply dampening. So within the game, if I release my touch event, the spaceship slows down and it stops. And of course, you'll know from Newtonian physics, unless in space there would be no resistance, it would carry on at a constant velocity in a straight line normally. But we don't normally want it to do that. So I want to have a way of simulating dampening or reduction in velocity. So what we do there is that, very simply, very crudely, is that each frame we are retaining 95% of the acceleration and we're losing 5%. And for the angular velocity, we're retaining 75% and we're losing 25% of it. So this will act to bring the acceleration and the velocity down to 0. And that's for the angular velocity, angular acceleration, and ditto for the acceleration and velocity. So it dampens things, it brings them to a stop unless we're providing input, and that's normally what we want. We don't want it to be too abrupt, well, probably, depends on the game. So there, that will sort of slide to a reasonably quick stop, but not an overly abrupt stop. At this point down here, we have got our input, we've given acceleration, we've updated our angular acceleration, we've dampened things down. We call the superclass then, so we use our acceleration to update our velocity, to update our position, for its position and for its angular movement. So that's all the player does. For the AI spaceship, this is a little bit more involved in terms of steering behavior. So again, it's a type sprite. We've got a couple of different types of AI behavior. One's the turret behavior, it sort of looks towards the player. Others, the seeker behavior, tries to seek out the player. And I'm remembering what type of behavior this AI entity uses. If we are, and we are in this case, we're going to separate, we're not going to try to avoid colliding with things. We need to have a distance within which we want to avoid. So remember, my world's 1,000 by 1,000. Objects generally are 50 by 50. So there we're saying that if we get within 75 units distance of a other ship, we want to try to move apart. And if we get within 125 distances of an asteroid, we want to move apart. These are center distances, so you need to take into account how big the objects are as well. For separating, when we're looking at separation, for this one, we're going to design it that it will try to avoid the player and asteroids and other ships and other turrets and things like that. So potentially there are lots of different things that we will be trying to avoid, and each of them will give us an acceleration away from the player or away from the asteroids. So we're going to have to accumulate or output acceleration. We're going to be having potentially different inputs into it, and we want to add them up. So we're going to have an accumulated acceleration and then a component one. So any time where we do a specific separation test, we'll store it as a component and we'll add it to our accumulator. But you'll see that below. When we're creating the AI spaceship, all we do is we're passing in here where it's located, what type of behavior we want this thing to have, and the screen to which it belongs. So there we're saying, okay, give its location, 50/50 size. We're not specifying the bitmap at this point, but we are specifying the screen. We remember the behavior, and then we do a switch on it. So if it's a turret, for example, we're saying that you can't accelerate and you can't move. There is no movement for you, but you are allowed to rotate. We do know the bitmap at this point because we know it's a turret, so we say use this bitmap, please. If it's a seeker, then we give it maximum accelerations, angular and velocity, and all the normal parameters, and what bitmap it should use. And then it's set up at this point. After this, we have our update, and there's no draw at the bottom, so we're making use of the draw that Sprite provided us. It's sufficient. Within the update here, you might think, oh, there's a fair amount of stuff. It's fairly repetitive. We're doing a switch. If it is a turret, then the only behavior that it has is that it looks at the player. So we are going to, our steering behaviors, we'll look at the library in a second, we're calling the Lookup method, and this takes in an entity, a sprite, so we're passing in ourselves, and we then have to pass in a position that we want to look at. And the position that we want to look at is the player's position. Now, how do we get the player's position? And this is something we've had to build into it. This object, in and of itself, it doesn't know the location of the player. The player and the AI-controlled ship, they both live within their particular game world, within the particular steering game screen in this case. So what we are doing there is that we know that we belong to a screen. But we're saying that it's not just any old screen, it's a steering demo game screen. So we're casting it to a steering demo game screen. The reason we do that is that steering demo game screens, they define a method called getPlayerSpaceship. We added that in when we created that particular game screen. And that gives us access to the player. So by doing this, we get access to the player, and we can then say, well, give me the position then of the player. So we need the position of the player. This gives us a way of enabling that information to be shared between our objects. And quite often you have to do that if AI needs other information in which to make decisions. Seeker behavior then. So what we are doing there is we are seeking towards the player. And very similar behavior. We're going to our library, we're calling the seek. We're passing in an object. So this is the thing that's doing the seeking. We've got to seek towards a position. So it's exactly the same way of working out the position. Go to our game screen, which has happened to be a steering game demo. Get the player's position. And what we are outputting from this method is an acceleration. So it's not simply returning a single scalar value. It is updating that vector to the x and the y location. So it gets to be updated. That gives us the seeking behavior. We then want to try to avoid whacking into things. So the first thing we check for is the player spaceship. So we are calling our separate behavior. So again, part of the library. We have the thing that's trying to be separating. And there's different versions of this. You can pass in just an object, another sprite you want to remain separate from, which we're doing here. We happen to be passing in the player spaceship. We say how close we can get before we want to separate, and with what strength are we trying to separate. And we are storing this as part of, if we have a value there, it's just going to be one component value, and we add it to our accumulator. So there can be multiple things we're adding to the accumulator. We also don't want to collide with the other spaceships. So we're going to our steering, we're calling a separate method. This one takes in different parameters. So it takes in, again, the object that's trying to avoid it, and a list of other objects. So this parameter is a list of sprites. How do we get access to the other AI-controlled spaceships? Similar process. We go back to our game screen. We've added in a method there called get AI spaceships that returns a list of them. So that's what we pass in. Separate threshold, how strong we're separating. And again, that gives us a component output. This will be a component output to avoid hitting other spaceships. We add it to our accumulated value. And we do exactly the same thing then with the asteroids. Now, we've got a couple of options here. I'm always going to have a seek acceleration because I'm always seeking towards the player. I may or I may not be close to the player, other spaceships, or asteroids. So I may or I may not have an avoidance acceleration. And I check to see, have actually I accumulated anything within it? Is it not 0? So if it isn't 0, it means that actually, yes, there was something I wanted to avoid hitting. Now, I could simply take this and add it on to the seek acceleration. And if I did that, if I just simply added it on, what I'm basically saying is that it is as important to seek towards the player as it is to avoid a collision. I'm giving each of them equal weighting. But I don't want to do it, and I'm not doing it here. What I'm saying here is that it is more important to avoid a collision than it is to seek towards the player. So my new x acceleration, let me just put it all in one line, maybe easier to see. My new x acceleration is equal to 30% of the steering acceleration plus 70% of the avoidance acceleration. So we retain most of the avoidance with a bit of the seeking. So we will still try to seek. We're not going to completely ignore that, but we will try stronger to avoid than we will to seek. At this point, we've got our acceleration. This is good. Finally, we work out our angular acceleration because we want to look in the direction of movement. So again, we call that behavior, and that's it. Then we're calling our super class method at the end that applies the accelerations to give us velocities, to give us updated positions and orientations. So that's it. That's how that one ties together. The last thing we need to look at is the library that these things have been calling. And this is basically a collection. It's not intended to, this is not something you intended to instantiate. All it contains is a collection of static methods. So all the methods within this are declared to be static. So there are things that you can call just for doing steering behaviors .seek or whatever. The types of stuff we have there, we'll go through it very briefly. It is basically implementations of the stuff that we looked at within the lecture. So I don't need to go through the precise coding because you can map that onto the lecture yourself. So for example, for seeking, we've got the sprite that's seeking, the target is seeking too, and then we need to output an acceleration. Java doesn't let you pass values by value or by reference. We don't want to create a new acceleration within this because that means that every single time I call this, I definitely don't want to return a new vector2 object because it is actually an object, which would just mess up garbage collection. So the particular pattern I'm using here is that you could pass me in this, you'll pass me in that, and you'll pass me in the acceleration. Now, I'm allowed to change the properties of the objects of this, and I will change the properties of the acceleration as my output. So effectively, I'm not returning anything, but I am updating one of the properties that were passed in. And we're doing that because we don't want to create any objects when we're calling this because it'll just kill performance. I got a first one, you can't seek towards yourself if you already are where you want to be. So just in the off chance, it's highly unlikely because using floats here, just in case the two things match, I will return a vector of 0. If they don't, then we initially set our acceleration to be a vector telling me the differences between them. So this is a vector that basically heads straight towards the target. I normalize it, bring it back to length 1, and I then extend that up based on the maximum acceleration that I've had specified for this particular sprite. So in other words, how fast can it accelerate in that particular direction? Let's move with that speed, or that acceleration rather. We've got flee, more or less exactly the same, except going in the opposite direction. We've got arrive then, and we are going to have a couple of temporary variables that we use within arrive, so for the direction and for the speed, because again, this is performance reasons. We don't want to create temporary objects within a method which then get to be discarded. So we are storing them up here so that we can reuse them. Doing that speeds it up, but it also means then you could have threading issues with this. You would not want multiple threads simultaneously calling the arrive method, as both of them could be accessing the arrive and speed at the same time. If you were doing that, you would want to tweak this, either to put guards on those or to use a different approach. Arrive is basically, again, what we looked at in the lecture. We worked out how far we are away from it. If we're within the slowing down radius, how fast do we want to travel to it, depending on how fast we are, and we then determine an acceleration that will give us that particular target velocity. So same as what we looked at in the lecture. We've got alignment here, so this is a similar thing where we're looking at something, and we've got our default smoothness value, which will determine how prompt or how strong the alignment happens. So again, for these ones here, you can see there's two versions of a lot of the methods. We got one here, we can align this sprite with this target orientation, and in this case we can align this sprite with this target orientation, and we take in a smoothness factor. So you can specify the smoothness value if you want, but if you can't be bothered doing that, you can also use the default smoothness. So it's just a way of giving you a little bit of flexibility on it. And all this one calls is the aligned version, takes in the smoothness, passing in the default parameter. For the align, where we're aligning orientations, so we have a little bit of tweaking of code here because angles loop around every 360 degrees. So we want to put every single angle into a standardized range. So everything is all in that same range. Other than that, it's more or less the same as arrive, working at our target angular velocity, and then what is the angular acceleration that would give us that angular velocity. There we have the lookup delegate behavior and align with movement delegate behavior. So in this case, we're not aligning with a target orientation, we're looking at a position. So we're using our Mas arctan2 to work out what is the orientation towards that point, and we then align with that orientation. Just as a reminder, a lot of the Android stuff, it assumes you're working in degrees. A lot of the Mas libraries assumes you're working in radians. If I do mas.arctan2, the angle I get from this is in radians, so I have to remember to turn that into degrees. Always be very careful about that. I can understand why within Android they're using degrees because it's easy for us to think about them. Most Mas though assumes radians, and if you're calling mathematical functions, you need to make sure you're appropriately using the right units for calling them or changing the results. Line with movement, you only take in the sprite. There we're using, again, arctan2 on the velocity that we have, and that's what we are aligning ourselves with. Here we have our separate method. So again, we've got a temporary separate acceleration variable used within it. Worthwhile having a little look at the constructors of this. So we've got the separating sprite, and you may or may not have seen this particular form. We're passing in a list of target sprites, and if I simply did list of sprite, and within my my game, so for example, where's my game? Down here, where I declare up here a list of asteroids. Now, asteroid is a type of sprite, So you might think, sure, it'll be passed in there perfectly fine. It won't. It will complain. And there's sort of a couple of reasons, reasonably sensible reasons, why if you declare a list of something, it has to be tightly bounded to that particular type. So a list of sprites must only be a list of sprites and not a list of asteroids or other things that extend it. How then do we say that we are prepared to accept a list of sprites or a list of anything that is a type of sprite? That's where you use this particular notation here. So we're taking in a list of something, and that something extends sprite. That's what you use. So just as a reminder, if you have this, it would have to be a list of sprites and nothing else. This is a list of anything, but it's a type of sprite. So it's a little bit more flexible. Passing it in, again, it maps onto the lecture stuff, so you're iterating through, you're working out the distances. Again, we're using square root values here to avoid doing square root calculations. Getting an accelerating acceleration from that, and then returning that. Another separate one at the end, so that this one we had up here separates from a list of objects. This thing down here separates just from a target object. So if it's not in the list, you don't need to stick it into one. You need to separate it from it normally. And that's it. It's only a subset of the steering behaviours that we looked at within the lecture, so feel free to modify, extend, enrich this particular one to add in whatever other steering behaviours you want to. So that covers this particular demo. It's been a reasonably long one in terms of the amount of stuff that we've looked at, but hopefully of use. The steering algorithms give you a very solid foundation in which you can sort of bring out a lot of different forms and styles of movement.